Good morning. I'll be talking about some of the grain storage issues that we face in Western Canada and how do we tackle them in my talk today. My background, I don't think I need, Kevin has given a very nice introduction. So I'll just move on to the harvesting and storage challenges here. Grain spoilage, safe grain storage, smart grain management using digital technology, and then I'll summarize some of my findings. So moving on to the motivation. So my big motivation is the food security issues that around the world. So what food security is? As per the World Health Organization, it's sufficient, affordable, and nutritious food for everybody on this planet, I would say, which is not possible without have sufficient production of the grains, including cereals, oil, seed, pulses. These are some of the numbers. We have currently about 7.6 billion population, which is going to be 9.8 billion by 2050. That means that we need to increase our food production by 50%. And that means that high pressure on natural resources and sustainability of the food system. Currently, we produce about 2.6 billion tons of grains, out of which from 10 to 30% losses occur everywhere, which could feed additional 1.3.5 billion people. And these grain losses occur during production, storage, handling, and processing, and they vary from throughout the supply chain in a different part of the world. In Canada, Western Canada, or more so in Alberta, we have seen one of the worst harvest season past year. And these are some of the headlines that you would have seen in the media. Harvest from the head. Disastrous harvest crop in Alberta. Alberta farmers grapple with the miserable harvest. So this is very real and just happened. These are the headlines a couple of months or weeks ago. Weather is not often favorable in Western Canada or Alberta for the harvest. We have usually a cold harvest season, wet harvest, and often like last year we have very early snow that creates a big problem for harvesting. This is the Alberta crop report here that you can see that as of November 5th this year, we had 11% of the crop was still left standing on the field. 17% canola crop, 15% potato crop, and 45% sugar beet crop was still on field. So these losses estimated were about $700 million in Alberta. That's huge. Other than the weather, then we have many trade barriers. Here in this picture, I don't mean to show anything other than the issue with the canola in China import. But there are many trade barriers, like tariffs. And for example, in India, they had increased the tariff on pulses last year from somewhere 30% to all the way 66%. Then we have MRL issues, we have quarantine issues. And so these, then biosecurity is a major one. And these are used often to, for negotiation, and there are many disputes to resolve them, and that takes time. So what that means is that we start with a bad harvest, and then we store it, that crop, and then due to these disputes or trade barrier issues, we try to hold it longer. That means that our grain spoilers risk on farm or even grain handling facility, that increases due to all these issues. So what is grain spoilage? Grain spoilage can result into the weight loss, quality, nutrition, seed, viability loss, and obviously reduction of the grade and the price, economical loss to the producers. Mold in the grain may produce carcinogenic mycotoxins, making the grain unfit for consumption. Insect cause significant post-harvest losses of 9 to 20% that study showed. Heat of respiration from the grain and molds may cause development of hot spots, and that is a real problem if you are holding wet grain into your bins. This is an example that happened, I think, 2016, that bin caught fire. That's another example that happened in Denison, Iowa. My data, I work in Canada, US, Australia, so some of my slides will have the data from different regions, but their fundamentals remain the same. So what these suggest that these two have caught fire. There was no sensing cable or measurement that we can say that caused, but most likely it was initiated by hotspot development. So this is the data that I got from a site in 2014 out of US Midwest, and you can see here that the highest temperature that we recorded was 60.8 degrees Celsius, and this is real-time data from a corn bin back in US. So this suggests that that it could initiate the hotspot and then all the way up to the fire. So it's quite challenging to manage the grain and then store long term. So what is a safe storage? It refers to the storage of grain for longer periods without any significant spoilage. Stored grain changes physically and chemically, and particularly canola. So you can have canola at 10% or even 8%, then still you can see that temperature rising due to the internal physiological changes into the grain. Temperature and grain moisture are two most significant factors that determine the safe storability of the grain. And they are also part of the best grain management practice. If you have a bad crop, mature grain, damaged kernels, unclean grain with more fire material has relatively shorter safe storage period. Safe storage is also cumulative. So if you start with a bad crop, high moisture, high temperature, and then you try to cool it down, dry it, but your total time, the storage is cumulative. So you have to consider those factors from the beginning, post-harvest conditions. Fortunately, we, like in many other agriculture fields, this digital technology, the new development in sensing technology, cloud computing, cloud platform, automation, this can also help at better managing our grain for longer safe storage. So this, the way I categorize or the way I look at it is you can divide into the 4 categories. One is the monitor. You monitor your crop regularly. You don't have to go and climb into the bin, but you use the technology. Modify the physical factors. And 2 of them important ones are moisture and temperature. So modify means you can dry the grain to reduce the temperature, moisture, and cool the grain to increase the shelf life of the grain. Then treat. So if you monitor, and then you can use the treatment as a control method to eliminate any spoilage risk. And the other component is not more, now the growers can use some of the modeling tools. So they don't have to be a mathematician, they don't have to develop mathematical model. But with cloud platform, they can just simply enter some of the inputs that they have, and then the machine should be able to run the simulation and give them output as a potential spoilage risk or the recommendation for longer safe storage period. This is what a smart grain management system looks like. So this is a vertical steel silo, very common in North America. Anyone is storing grain for longer periods should have temperature cables, that one vertical suspension cable from the top, moisture cable so that you can measure moisture in real time. Then also there should be a fan, aeration fan installed, and then you can measure the plenum pressure, temperature, a local weather station, head space temperature, and humidity sensor. And you can assess all using on the integrated on the cloud-based platform. So you can use your tablet, your iPhone, or desktop computer from anywhere in the world. So for example, I have still my students in Australia. He's working on towards his PhD, and I remotely log in from here to a grain silo if he wants to look at the grain condition, or if you want to change anything, any controller. So you can do the same thing sitting anywhere in the world as long as you have internet access. So first I mentioned the grain monitoring. It's very important, as grain is always susceptible to spoilage due to self-heating, condensation, mold growth, and insect infestation. Monitoring of grain moisture, temperature, insect activity, CO2 level, and phosphine are vital to develop best grain management practice and take corrective action if you see something is going wrong and your grain storage bin. Grain monitoring not only ensures safe storage, but also provides early warning, as I mentioned, so you can take corrective action before you see some fire coming or smoke coming out of the bin. Also, there's this data from the grain bin through this sensing technology. Or you can develop the automated aeration fan control and also later on, so that there's not any guesswork. All the controls are based on the real-time grain conditions inside the silos. This is an example. This was a bin of further north of Edmonton and stored canola. Canola was harvested at 26 degrees Celsius, and then after 8 days of storage, it reached to 30 degrees Celsius. And after next 4 days, from 30, it reached to 40 degrees Celsius. But with this technology, the farmer was looking, and this was a hopper bottom silo with no aeration fan. But the farmer was tracking the temperature change, and then at 40 degrees Celsius, then that's really a concerning condition. So what he did is that he moved the grain, because there's no aeration, so you cannot cool, but it's a smaller bin, you can move the grain. So he moved the grain, unload it, and then put it back. So due to the cold conditions, it cooled down the grain. And then thankfully, he had no issue, and then he confirmed that on June 15th in the following year, he sold as canola number 1 at 8%, 4% moisture without any discount. So you can think if you have no monitoring in this bin, it could have been turned into the one at the very first bin that I sold, what happened to the canola bin in Saskatchewan. So that's why technology is helpful. This is another data from all these lines are the different sensing sensors in a cable in vertical structure. So you can see in that the peak that happened all of a sudden, they had the fan failure. So the cooling stopped, and then all of the sudden temperature rises to about 58, it's in degree Fahrenheit, 138 something, I recall the data, but it's about 58, 59 degrees Celsius in that canola bin. So again, then they use the aeration, cooled it down to almost 5 degrees Celsius, and that's how they manage. So this is the way technology is helpful again. And monitoring. Often here, the recommendation is to cool the grain during for the winter holding time. So if you have no control, people just run the fan, and then not just the cool, but sometimes freeze it to -5 or -10 degrees Celsius. What happens in early spring or in summertime, sometimes by mistake they turn the fan on, or due to the solar heating, from the wall of the silo, it starts to heat. And that heat circulation inside the silo creates the condensation. And same thing will happen if you blow the warm air in a cold grain. And that condensation and water accumulation again creates a problem. And if you don't have any monitoring, you don't see it. So this is, but with monitoring you can see it. So this is another data. I'm not sure if those numbers you can see. But again, more than 40, 45 degrees Celsius temperature. But they were able to track and then slowly warm it. So use the aeration fan, not too hot air, but pick the good time and then slowly warm it, gradual warming. And that allows any condensation or picks the moisture that occur due to the condensation into the grain. So next is modify, how we can modify the grain moisture, physical conditions, which are temperature and the moisture. So drying and aeration is common, but you need to be careful while doing this to avoid any failure in grain management or any spoilage risks. But dry and cool grain is the key to the long-term safe storage or the grain management practice. If you have the drying capability, you can do early harvesting, and that eliminates some of the weather risk if you can harvest the crop as soon as it reaches physiological maturity and can be dried. So the number one great moisture threshold or the cutoff upper limit is not when you should be harvesting. If you have the infrastructure in place, then you can start early harvesting. And in mid-natural air drying is considered the low cost and high quality in product drying. So your product is in better condition if you do not use any high heaters and high temperature dryers. And then dried grain can be aerated for winter holding for long term. So next issue in the drying and aeration is often talked when to operate the fan. And so these are some of the media highlights that I've just captured from the past. And if you are grain handlers or producer, you would have come across these debates. So there are different opinions. Run the fan continuously, that was often the practice, that just turn it on, no one is going to the farm and then checking every day. Or some suggestions came, turn the fan in, only drying should happen during the night time. And some suggestion, drying should happen during the daytime. So there's confusion around how we manage, how we dry and cool the grain. So automation is an option. You don't have to do it by manually driving to your bin and turn on and off every day. You can use automation and the system will take care of based on the conditions. This is an example that the data I got from Australia. They have different harvest conditions. Here we harvest, move into the winter, cold climate. They harvest and then they move into the summer. So they have a dry and hot summer, but they have dry grain. For example, wheat is coming into the silos, 8%, some often 7, 8, 9%. Always, I've seen always less than 10%. So they have insect and issue, but if they can cool here below 20 degrees Celsius, then that reduces the insect growth. Ideally, if they can cool it to 15 degrees Celsius, and that's the best grain management practice for that part. So here, the grain was almost up to 38 degrees Celsius initially, and then I used this automated system to cool it down. And as I mentioned here, this is the sensor temperature, grain temperature data, as well as the line that's fluctuating, blue line, the ambient conditions, and sometimes it's almost 40 degrees Celsius. So you cannot say day or night and time, just allow the system to pick the best time which air has cooling or drying potential. This is another rice drying, or rough rice, called often paddy, also in New South Wales, Australia. So we started this trial with initial moisture of almost 20%, 18 to 20% rough rice, and dried to 13.5%, and that's where the standard is for the milling. And we were able to dry to very uniformly, as I'm not sure if you can see these numbers, but we are almost in between 13.5 to 14% moisture range in that. And also in this, we did comparative studies. So the next shed that we use in here, we allowed them to manage on their own by the way they used to do in traditional way, on, off, day or night. We didn't give any suggestion or did anything. So we almost managed, compared to they were down to 12.4, 12.5, where the target is 13.5. So we almost managed 1.5 to 1 to 1.5% shrink. So and we can calculate that how much turn into the saving based on your storage capacity. The next is the modeling. So how we can use mathematical modeling into the grain storage management. And this is another data that one of PhD students is working on it. The top one shows that how we can measure the airflow, the pressure distribution inside the grain silo when you are blowing the air. And this is not a full floor perforation bin. This has two ducts in the V-shape, that the channels that's blowing air through the planer. The bottom one shows the airflow velocity, how the airflow is moving. So as you can see, the top core in the clone, the darker blue, we have almost zero velocity. So that means we cannot do any cooling in that, and that's where the hot spot is most likely going to initiate. So we can model and see based on our fan capacity, and then we can suggest changing either fan or the planar perforation, or redistribute the air that's going into the bin. So we also did the validation for that, the modeling work, and this is the same silo that I had shown you aeration data. In the center peak, as expected, we could not measure any airflow rate, almost negligible. So our anemometer we used, we amplified using funnel, nothing we could not see. As we move more towards the AU, we got almost 0.11 CFM per percent. That's the minimum requirement for aeration. And if you're thinking of drying in a grain bin, it has to be 10 times more, because cooling front moves much faster compared to drying. So you're supposed to have 1 CFM per bushel. So if you're thinking of drying in this bin, it's going to be a disaster. You cannot achieve any drying. There's not enough airflow rate. So that's how the modeling can help redesign system or evaluate the potential cooling or drying in a particular grain bin with the current aeration system. This is another slide of the drying simulation that you can use. And this work I did when there was a talk about 4 or 5 years that this debate came, nighttime drying, daytime drying. So this looks a little bit overflooded, but I'll try to explain, and then I can discuss this later on. So what in this, I use 3 blocks, 3 initial conditions. Harvesting, you are harvesting the wheat at 20% initial moisture content, then 18% initial moisture content, and 16% initial moisture content. So these are the initial conditions. And also, you can start early harvest. August 20th, I picked one condition, that's the green bar. The next one is September 1st, and then September 15 is the third one, blue one, and then the next October 1st as the fourth one, the start date for your drying. So these are the days when you would load the grain into your bin. Other than that, I use 5 different strategies, if you can see. First one is the on strategy, that you just load the grain and turn the fan continuously on. The second one was the day you only operate the fan during the daytime. The third one is nighttime only. The fourth one is natural air drying, which is automated control. And the last one is self-adapting variable advanced control with the heater. And this, I use 20 years of data from 14 locations in Western Canada, in Alberta, Saskatchewan, and Manitoba, to run the simulation till the end, for 45 days, up to 45 days, to see what happens. So if you look at those bars, there's a red line, that's your target, that's where you want to be. And how is much, the higher you are, that shows you are, so the bar shows you your spread in the moisture. So you finish the drying, you completed 45 days of drying, and where are you sitting? So the yellow line you go at the top is almost 18%, and the lower range is of 12%, for example. So that shows your spread of the grain in the bin. That's no good, because the bottom you dried maybe a few layers at 12 or 13%, but top is still sitting at 18 or 19%. So this is the way that you can run simulation and see where is drying potential. What is, obviously, if you look at the way right side, that it's much more narrower. The spread is much more narrower in all the bins, because you are harvesting at lower moisture content grain. So in drying, you have to remove 4 to 5%. Whereas in the way left side, you are starting with high moisture and 20%. So that's why you are not able to achieve the drying or more uniform and tight spread into that condition. So these are the things that simulation can use. And now with the cloud computing capability, this model can be implemented online, and the users or growers, they can just say, okay, this is my starting initial moisture content, this is my grain type, this day I'm starting, this is my airflow rate that I have, and they can see what they can do, how they manage, what are the spoilage risks to their grains. So with this is my last slide. I would like to summarize. The post-harvest grain loss can be significantly reduced by smart grain management technology. As I showed in my presentation, growers can make informed decisions to avail the best marketing opportunities based on the grain condition and the risk that they have. That can help them increase their profitability through quality optimization, moisture control, energy savings, reduce operating costs, detection of contaminants, and prevention of spoilers. This I would like to thank Lethbridge College for supporting my research program that I started a couple of months ago. I'd like to also thank University of South Australia, OP Systems, lots of data shown here through their systems, and GRDC, which funded my research back in Australia. Thank you. Any questions, please?
Thanks very much, Chandra. Questions? Grab a microphone or wave your arm and I'll bring the mic out and entertain questions. Chandra, I was trying to follow along and I realized, I think it was Ron Palmer that did the work at Indian Head, and the recommendation, and I was there when he first presented it at an applied research day, and everybody went, oh wow, that's really neat. Turn your fan on at night. You know, put the grain in the bin, leave the fan on for the first couple days, but after that, just turn it on at night. That's when you're going to remove the most moisture. And then PAMI came out, and Joy Agnew seemed to counteract that and say, no, that's not the approach. And I saw all the data there, but I still can't figure it out. What's the right approach? Leave the fan on all the time, or turn it on only at night, or get some sort of automated system that's going to tell you what to do?
Yeah, so the automated system is the best way to deal with. It removes most of the guesswork, and it's an intelligent system, and it picks the best cooling or drying opportunity based on the ambient condition that's available there. So if there's no good condition, it will not turn it on. But if there's any, with the drying, below 5 degrees Celsius, the air has no drying potential. So no matter whether day or night, you cannot dry. His approach was, partially he was right, because when you harvest, due to the respiration, the grain is hot, and you blow the cool air, and then due to that evaporative cooling, you eliminate 1% moisture, maybe max 1.5% moisture. And that you can see that here too. So that's the maximum you can do with that approach, but as the temperature equalizes, the grain and air reach the same temperature, there's no evaporating cooling potential in there, and then you have to pick air with lower relative humidity or EMC value, and that's how the system works.
So the automated system, what all does it measure to decide whether the fan should be on or off? What all goes into it? The outside relative humidity, the outside temperature, as well as the moisture and temperature of the grain?
Exactly, yes, yeah. And not just the moisture average, but the SAV, the loss control that I mentioned, it's self-adaptive. So it looks at your bottom moisture also, which often you over dry, and then it also rehydrates. So it picks the moisture, okay, let me be more aggressive, over dry the bottom part, and then pick the little bit wet moisture, and then bump that up. So you're more tight to close to your target moisture.
Okay, some of us that don't have full-fledged grain dryers, and I think across the southern prairies, that's not uncommon to not have a grain dryer. I've got aeration fans. I've got a propane burner on one aeration fan. I'm tempted to get one of these construction heaters and hook them to a couple of aeration fans for falls like this, when things when you need every advantage you might get. What about adding supplemental heat to an aeration fan? Good idea, bad idea? What should you look at?
Yeah, I would recommend in these conditions, that's the last one, it has that's the SAV is controlled. It has supplemental heat, but again, any system, in some days it's dry, you don't need heater to turn. So it will also pick when to start the burner or heater, based on the ambient condition in grain, it will automatically pick the burner. So you're not continuously running the heater. It's only the conditions, a part of the day. So for example, early morning you need the heater, not into afternoon. So it will calculate, do I need heater, or my ambient air has good EMC with the drying potential.
Okay, now I haven't gone to the stores to look at this, but what does it cost to put that sort of an automation onto a system? What is the cost?
just the automated system, it's 3 to 5% of your all silo cost. That's what it comes to.
Questions for Chandra? Anybody got anything they'd like to bring up? With that, Chandra, thank you very much. Really appreciate it.